In this video, I'm going to graph a rational function. In particular, we're going to look at graphing a linear function over a linear function. So here's the function we're going to graph. F of x equals 2x minus 5 divided by x plus 1. We're going to do so by finding these 5 things. If you notice, these things are basically the same things we did when we did a rational function with one exception, and that being the zeros. So anytime I'm doing a rational function, f at x, I'm going to refer to the numerator as p at x and the denominator as q at x. So in this case, p at x is 2x minus 5, and q at x would be x plus 1. So the first thing I have to do is find the zeros or x-intercepts. So hopefully we know the way you get the zeros is to set f at x equal to 0. So in this case, f at x was equal to 2x minus 5 all divided by x plus 1. And that's going to be equal to 0. So now the question is, when does this fraction equal 0? And the answer to that question is, when would a fraction be equal to 0? So a fraction is going to be equal to 0 whenever the numerator is equal to 0, right? Because 0 divided by something is equal to 0. So all we have to do is set p at x, or the numerator, equal to 0. So 2x minus 5 equals 0. So solve for x. So 2x equals 5, or x equals 5 over 2. What that means is if I subbed 5 over 2 into this equation, the numerator would be 0, and I'd have 0 divided by something, which is equal to 0. So therefore, 5 over 2, 0, is the x-intercept. Okay, the next thing we look for is the y-intercept. We do that the same way we did polynomials or reciprocal functions. We just evaluate the function at 0 by letting x equal to 0. So that'd be 2 times 0 minus 5 all over 0 plus 1. So we're just subbing 0 in for x. That's going to be equal to negative 5 over 1. So therefore, which is minus 5. 0 minus 5 is the y-intercept. So the third thing we're going to look for is vertical asymptotes. So f at x was equal to 2x minus 5 over x plus 1. So now the question is, when do vertical asymptotes occur? And vertical asymptotes are going to occur whenever this function is undefined. So that would be whenever the denominator, or q at x, is equal to 0. So take the denominator, set it equal to 0, and that would be your vertical asymptote. Now, just to make a note, in regards to vertical asymptotes in zeros, so zeros occur when the top is 0, and vertical asymptotes occur when the bottom is 0. The one thing you have to be careful about is you must simplify first. So if there was a common factor on the top and the bottom, and that value gave you a 0 for both the numerator and denominator, that wouldn't give you a vertical asymptote or a 0. That's actually a special case that we could talk about. We'll talk about in another video. But in this case, this is in lowest terms. So that would be the vertical asymptote. The fourth thing is the end behavior. And if you haven't already done so, make sure you watch the video on end behavior of rational functions where we developed the rule for the end behavior. So I don't need to write it again. We figured out in the previous video that as x goes to plus or minus infinity, y will go to, in this case, because the degree is the same for p at x and q at x, it just goes to the quotient of the leading coefficients. In this case, the leading coefficient is 1. So it's going to go to the quotient of 2 over 1, which is just 2. So y goes to 2. That's because it's a linear function over a linear function. This would be true for any two linear functions. You just take the quotient of the two leading coefficients. So therefore, the horizontal asymptote is y equals 2. And the last thing is positive negative intervals. So for positive negative intervals, remember f at x was, what was it? It's 2x minus 5 over x plus 1. You're going to set up a interval chart or interval table starting at minus infinity, going all the way to infinity, and you're going to break it into intervals which are separated by the x-intercepts, which was 5 over 2, and the vertical asymptotes. So in this case, x, or the restriction was x cannot be negative 1. So these two numbers are going to go into your interval table. The smallest one goes first, which was minus 1. 5 over 2, 5 over 2. Then you can list the factors here. 2x minus 5 and x plus 1. And the quotient of those two things gives you f at x. So now I'm just going to take a number in the interval from minus infinity to minus 1. So let's say minus 10, and test that value in these two intervals, for these two factors. Both cases, if I subbed in a number, x equals minus 10 into this factor, I would get a negative number. And here I would also get a negative number. If I took a number between minus 1 and 5 over 2, say 0, and I subbed it into this factor, I would get a negative, and this one I would get a positive. And if I took a number bigger than 5 over 2, both factors would be positive. So now f at x is the quotient of these two things. So the quotient of two negative numbers is a positive number. Quotient of a negative and a positive is negative, and quotient of two positives is positive. So therefore, f at x is less than 0 if x is in the interval from minus 1 to 5 over 2, and f at x is bigger than 0 if x is in the interval from minus infinity to minus 1, or 5 over 2 to infinity. Okay. Now we're going to graph this thing. Too far. So draw your axes. Try to make them straight. So using a ruler would always help here. Once you have your axes, you have to put your scale on. So make sure your scale allows you to graph the key points. We had minus 1 as an asymptote, so definitely need that. 5 over 2 was our x-intercept, so minus 1 was our vertical asymptote, so x equals minus 1. 5 over 2, so 5 over 2 is 2.5. So that point's going to be important. What was our y-intercept? Go up to our y-intercept, 0, -5. So we'll have to have -5 on our y scale. So that'd be -5. So we have these two key points, and those are the only two key points we have. So it makes it a little bit trickier to have fewer key points. Now we just have to look at our positive, negative intervals. So remember, it was positive to the left of the x-axis. So it's going to be positive over here, negative between -1 and 5 over 2. So negative here, and positive to the right of 2.5. So let's do this in sections. So here it's positive, meaning it's above the x-axis. I don't have any key points, which makes it a little bit trickier to graph, but I do know there's a horizontal asymptote of the y-axis and a vertical asymptote of x equals -1. So if it's positive, the only way that that could happen is for it to look something like this. I'm not sure exactly like where this point or where these points would be, but I do know that the curve has to approach these two lines on this side of the x-axis. Now over here, I know between -1 and 2.5 is negative, which is good because I have a well, let me just take it back a second here. Don't want to redo this whole video. I did miss something. So what I missed was my horizontal asymptote. My horizontal asymptote was, of course, what was my horizontal asymptote? 2. We had a horizontal asymptote of 2. So you, of course, have to put that on your graph. So that's 2. So y equals 2. So don't forget that. So that's not going to really change things here. It just means my curve has to, it wasn't y equals 0, it was y equals 2. If you caught that, good for you. Just making sure you're paying attention. And then over here, remember it was negative here. So it's got to connect these 2 points, and then this is a vertical asymptote, so it's got to go down and approach this vertical asymptote down here. And then it's going to come up, and it's positive in this section, so above the x-axis, and approach the vertical asymptote here. This part should look smooth, a little bit smoother than my curve looked, just like over here. Should be a little bit smoother than that. But that's generally what a rational function of a linear over a linear is going to look like.